Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this is the continuation of the calculating derivative theorems. When last I left you, you were working on this problem. I hope you finished it, and we'll check your work. But if not, you have an opportunity to catch up with us now so you know what to do. Let's see how you did. Now, one of the points of this problem is for you to realize that the derivative of a product is not the product of the derivatives. An easy way to see this is if this were x times x, that would be x squared, and the derivative of x squared is 2x. But the product of the derivative x and x would be 1 times 1, and so 2x does not equal 1. So that proves that this really is not a correct formula. Similarly, a quotient, the derivative of a quotient is not the quotient of the derivatives. And again, what you could have said is, oh, suppose I had 2x over x. Well, 2x over x would be 2, and the derivative of 2 would be 0. But if you took the derivative of the numerator, it was 2x, over the derivative of the denominator, which was x, it would be 2 over 1 is 2. So you see, neither of these formulas are true, and soon we will come up with the correct formulas for product rules and quotient rules, but they are not these. Now what that means for these problems is you have to do algebra first. And so what you will do is you will distribute this expression, x to the 2/3 across these. You'll be adding exponents and so on and so forth, and then after doing the algebra you will take the derivative. And when you take the derivative of this, you're going to use the rules that we had, and you will get 10 over 3 x to the 2 over 3 minus 8 over 3 x to the 5 over 3. Here, similarly, you're going to be dividing this t squared into each term in the numerator. So you're going to get 2t cubed, you're going to get plus 1, and minus 5t to the minus 2. After doing this algebra, you have the tool to take the derivative, so h prime of t is this expression. Here's an example 3. The question is, if this is a function, as it is it increasing, decreasing, or not changing at t equal minus 2? You know what to do. Let's see how you did. Well, increasing, decreasing, or not changing is all about the derivative. So we need to calculate the derivative of this function, and it is best changing that to a minus 3 to calculate the derivative. Then we will go through and we'll find out what f prime is. So f prime is this, and when you simplify, it could be looking like this. And now we're going to substitute minus 2 in. And when we do the calculation, we get a negative number, and that means the function has to be decreasing because the derivative is negative at minus 2. Here's example 4. We're supposed to find the equation of the tangent line to this function at the point x equal 16. This is a classical problem in calculus. I'm sure you will be asked this several times during this course. And so now's an opportunity to give it a go. Let's see how you did. Alright, so this is f of x. So f prime is going to be this. That's a minus 1/2. And so when I write it this way, I would have it this way. Now I have to substitute then 16 into this. That will tell me the slope. So when I substitute 16 into this expression, I get 3. So the slope is 3. To find the y coordinate, y is equal to f of x, I have to plug in the x is 16. To find out what y is, I get 32. So I use my point slope form or some other form, but in slope-intercept form, this would be y is equal to 3x minus 16. And here is example 5, where I'm in the position of an object at time t and hours is given by this expression s of t. Determine whether the object, or excuse me, determine when the object is moving to the right and when it is moving to the left. And I suppose that also tells you when it's changing directions. You know what to do. Let's see how you did. Well, the direction is a function of the velocity. So if this is the position, then the first derivative with respect to time is the velocity. So we'll take the first derivative of this with respect to time, and we get this. Now we do need to factor this, and you'll see why in just a moment. Because you see, if the velocity is positive, it is moving to the right. If the velocity is negative, it is moving to the left. Now, since polynomials, and this is a polynomial, are continuous, we know from the intermediate value theorem that if the polynomial ever changes sign, then it must have gone through 0 first. So we know when the derivative was equal to 0, we would know these are the only points where the derivative might change signs. So we set this equal to 0, and we say, oh, that's going to be 0 at x equal 2 and x equal 5. So those are the only places where this can change sign. So now what I can do is I can take a test point in this interval here. I take 1. I'll take a test point in this interval. I'll take 3. I'll take a test point in this interval. I'll take 6. And I find out that it is positive. S prime velocity is positive here. It is negative here, and it's positive here. It does not always alternate this way. It really depends on the nature of the polynomial, but this one does. So the intervals where the derivative is positive are these two intervals. We're not going to discuss right now whether time could be negative or not, but this is those are the intervals, and so those are where it's positive. That means it's moving to the right in those, and between 2 and 5 it is moving left. An interesting question for me to ask, I'm not going to do it right now though, would be how far did it go from 0 to 7 or something? How far did it travel? And counting left and right would be still distance that it would be traveling. There is a 14.2, but I'm closing now. So in closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless y'all.